When we talk about artificial intelligence systems that perceive the world, we are usually talking about systems that convert raw sensory data into structured representations. Two of the most important examples are speech recognition and image segmentation. In one case, the input is an audio waveform and the output is text. In the other case, the input is an image and the output is a pixel-level labeling. Both problems illustrate core principles of modern AI architecture: representation learning, probabilistic modeling, sequence modeling, spatial reasoning, optimization, and generalization. Let us begin with speech recognition. At its core, speech recognition is the problem of mapping a time-varying acoustic signal to a sequence of linguistic tokens. The acoustic signal is a continuous waveform, usually sampled at 16 kHz or higher. This means we are dealing with tens of thousands of amplitude measurements per second. The output, however, is discrete, characters, subword units, or words. The first important point is that speech recognition is not simply a classification problem. It is a structured prediction problem. The input is a variable length time series, and the output is a variable length sequence. There is no simple one-to-one alignment between input frames and output tokens. Speech is continuous and co-articulated. The acoustic realization of a phoneme depends heavily on context. Words blend together. Pauses vary. Speakers differ in accent, pitch, speaking rate, and articulation. Historically, speech recognition systems were built as pipelines. The raw waveform was first transformed into features such as mel-frequency cepstral coefficients, or MFCCs. These features attempt to approximate aspects of human auditory perception by emphasizing frequency bands relevant to speech. The idea was to compress the waveform into a representation that preserves linguistic content while discarding irrelevant variation. On top of these features, classical systems used hidden Markov models, or HOMs, to model temporal structure. HOM represents speech as a sequence of hidden states corresponding roughly to phonetic units. Each state emits observable features according to some probability distribution, often modeled by Gaussian mixtures. The model includes transition probabilities between states, capturing temporal progression. The fundamental principle here is probabilistic modeling. We want to compute the most likely word sequence given the acoustic observations. Using Bayes' rule, this can be expressed as maximizing the product of an acoustic model likelihood and a language model prior. The acoustic model estimates the probability of the observed features given a sequence of phonetic states. The language model estimates the probability of a word sequence based on linguistic statistics. Decoding in such systems involves dynamic programming, typically using the Viterbi algorithm, to find the most probable state sequence. This illustrates a broader AI concept: structured inference under uncertainty. We are not just classifying frames independently. We are optimizing over sequences with temporal constraints. With the rise of deep learning, the architecture of speech recognition systems changed significantly. Instead of handcrafted features plus Gaussian mixture models, deep neural networks began to learn hierarchical representations directly from raw or minimally processed audio. Convolutional neural networks can extract local time frequency patterns. Recurrent neural networks, especially long short-term memory networks, model long-range temporal dependencies. One key innovation was the introduction of connectionist temporal classification, or CTC. CTC provides a way to train sequence-to-sequence models without requiring explicit alignment between input frames and output tokens. It defines a loss function that sums over all possible alignments consistent with the target sequence. This removes the need for frame-level labeling and simplifies training. Later, attention-based encoder-decoder architectures emerged. In these systems, an encoder network processes the entire input sequence into a high-level representation. A decoder network generates output tokens one by one, attending to relevant parts of the encoded representation at each step. Attention mechanisms allow the model to learn soft alignments between input frames and output tokens dynamically. More recently, transformer-based architectures have become dominant. Transformers rely on self-attention mechanisms to model global dependencies in sequences without relying on recurrence. In speech recognition, A transformer encoder can process the entire time-frequency representation, capturing long-range interactions efficiently. The decoder, also transformer-based, generates text autoregressively. The architectural shift reflects a broader trend in AI, from modular pipelines to end-to-end differentiable systems. In end-to-end training, the entire model is optimized jointly to minimize transcription error. This allows representations to adapt to the final objective rather than being constrained by handcrafted intermediate stages. Now let us consider some core challenges in speech recognition. One is variability. Different speakers produce the same word differently. Environmental noise can distort the signal. Microphone characteristics vary. Robust systems must learn invariances to these factors. Data augmentation techniques, such as adding noise or simulating reverberation, help models generalize. Another challenge is language modeling. Even if the acoustic model is strong, the system must choose among phonetically similar sequences. For example, recognized speech and recognized speech can sound similar. The language model encodes prior knowledge about plausible word sequences. Modern systems often integrate large neural language models to improve fluency and grammaticality. Evaluation of speech recognition systems typically uses word error rate, or VER, which measures substitutions, insertions, and deletions relative to a reference transcription. A low VER indicates high transcription accuracy. However, VER does not capture semantic correctness or usability in downstream tasks. Therefore, evaluation must consider context.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.